in question 2 we have to deal with this compound, and the sensible thing to do is just identify the functional groups, just so that you are clear what we're talking about. So you've got an aldehyde, okay, carbonyl at the end of the chain is an aldehyde. That's a phenol where you have OH directly bonded to the ring, and that's a primary alcohol. And if you just keep in your head that that's what you've got, and you know about the chemistry of each of those things, then the question should be straightforward. So first it wants to know, what if you add 2,4-dinitrophenolhydrazine? Well, you should have learnt that that is a reagent which reacts only with aldehydes and ketones. So it's going to react because of the aldehyde group there. And the observation is that you get an orange or yellow precipitate. So that's the 2,4-DNP one. And that would have worked if it had any kind of aldehyde or ketone group. These two groups wouldn't have reacted with it. Then it wants to know what happens if we add aqueous sodium hydroxide. So that's about knowing about acidity. Okay, so in the A-level chemistry that we do, sodium hydroxide does two things. It can act, OH- can act as a nucleophile in nucleophilic substitution, but that's haloalkanes. We've got no halo group here, so that's not an issue. Or it can act as a base and take H+ away. So you've just got to know, are aldehydes acidic? No. Are primary alcohols acidic? No. Are phenols acidic? Yes. That's all. It's just a case that you've got to know the acidity story. You've got to know when it's possible for something to lose H+, and the story is that the phenol is acidic, which means that a phenol can lose H+, like this. And remember, it's a very weak acid, so it doesn't do this very easily, but it's a whole lot better at it than an alcohol or an aldehyde, which are negligibly acidic. But these the phenols can do this because the negative charge gets delocalized around the ring. Because that lone pair forms part of the delocalized system, the negative charge in effect gets spread around the ring, and that stabilizes it a bit. So you've got to ideally know that story about why phenols are acidic, but first and foremost you've got to learn that they are. So what that means is that when you add the sodium hydroxide, this won't react, that won't react, because they're not acidic, so there's no way the hydroxide can take H+ away, but this will react. And so if you add sodium hydroxide, the two groups at the top will be unaffected, but this one will form that. And so it didn't actually show you the sodium ion in the question, so that's the anion that's left behind. Okay, so that is just knowledge that you have to have. You know, phenols, there are really two things to learn about them. One is about the OH group activating the ring, 2,4,6 directing, all that stuff, and the other is this. So it's just learning the key things about the functional groups, and then these questions are quite manageable. So then it asks about Tollens reagent, and again, Tollens reagent, you just need to learn that it's a selective reagent. It reacts only with aldehydes. That's why it's useful, because it's a very specific test for aldehyde. So you know it's going to leave this group alone, and it's going to leave that group alone. So any suggested structures in which those were altered must be wrong. All it reacts with is the aldehyde group. And then you need to know a little bit about the chemistry of the test. So remember, Tollens reagent is a solution containing Ag+ ions in aqueous ammonia. You need to know that much about what Tollens reagent is. And when it reacts with an aldehyde, it forms a silver mirror, which means this reaction happens. So the silver is reduced because it's gaining an electron in order to form the shiny silver metal. So if the silver is reduced, the aldehyde must be oxidized. And if you oxidize an aldehyde, you get a carboxylic acid, which is that. So it's as simple as that. It's about knowing that Tollens reagent is selective, only reacts with aldehydes. That's why we bother learning about it, because it's very useful for distinguishing aldehydes from other things. And you need to know just that little bit about the chemistry. You don't need to be able to write detailed equations, but you need to know that it oxidizes aldehydes to carboxylic acids, and in the process the silver ions become reduced to silver, hence the shiny silver mirror. The next question asks about this reaction with aqueous sodium cyanide and aqueous acid reacting with your reagent. Questions like this should not be about you sitting there thinking, what on earth might sodium cyanide do to this? It's about learning the reactions so that you think, what reactions do I know of cyanide? And by the end of the A-level you will know 2. At the moment you know precisely 1, which is that it can undergo addition to an aldehyde or ketone in the presence of acid. And you just have to know that reaction. So you don't know any reaction of phenols with cyanide, you don't know any reaction of alcohols with cyanide, so there isn't one. Okay, that's the rule you have to stick to, that provided you've done your revision properly, if you don't know a reaction, there isn't one. So the one that does happen is addition. And so all that happens is that most of the molecule stays the same. So your phenol is still a phenol, your alcohol is still an alcohol, but you get addition across the CO bond. So this end becomes OH and this end gets CN attached. And that's the compound that you get. So then you have to convert that to a molecular formula, and again that's just practice. We'll make that a quick process. So first of all you count the carbons. So you've got 6 in the ring, 7, 8, 9 altogether. So it's C9. You've got 1 nitrogen, and you've got 1, 2, 3 oxygens. So the only bit that's slightly tricky is making sure you count the hydrogens, because they're the ones you can't see, all of them. So that one you've got, that's a CH2, so that's 1, 2, 3. Remember, in the ring there's just one thing on each corner, so there are 1, 2, 3 hydrogens there. So that's 6 so far. 1 on that carbon, because that's just got 3 bonds shown, so there's 1 hydrogen there, takes you to 7. And then these 2 on the OH groups takes you to 9. So C9H9NO3 is the molecular formula. Now that is one of the reactions for which you are meant to have learnt the mechanism. So the last part of this question should have been easy, provided you had done that revision and learnt the mechanism of the reaction. So that the name of the mechanism for addition to aldehydes and ketones is nucleophilic addition. So that was what you needed for the name of the mechanism. But let's just remind you of how that works, because you need to, although it didn't ask you to write the mechanism out, because obviously you couldn't really do that in the sort of format of question that we had here, you had to remember what happens in the mechanism in order to answer the last part about the rate equation. So let's remind you how nucleophilic addition works. So I'll just write the aldehyde like that, because I don't want to have to write out the whole rest of the structure, because that's irrelevant. This is the bit that reacts. And remember, what happens in nucleophilic addition is that you have a polar bond there, and cyanide is the nucleophile. Okay, a nucleophile is an electron pair donor, and that's got the electron pair ready to donate, so it does that. Okay, so the lone pair on the carbon forms a new bond to this carbon. That carbon has to let go of a bond, and it's the pi bond that breaks and becomes a new lone pair on oxygen. So you get then an intermediate, which looks like this. With the CN attached as well. Right, so that's our intermediate. And then, remember, you've got H plus in the reaction mixture as well. So in the second step, the H plus comes into play, and you get this. Which is your hydroxynitrile product. Now you need to have learnt that. You need to know in detail and be able to reproduce quickly, confidently, accurately that mechanism and the one for H minus attacking when NaBH4 is the reagent. And that's what this question depended on, because it said if the first step is the slow one, what will the rate equation be? So this is making a crossover now into the physical chemistry stuff. And what you learn in rates of reaction is that the order of reaction for a substance is equal to the number of particles, meaning atoms or molecules or ions, whatever it is, of that substance that react in the rate determining step. Now, we discussed why that should be, but in the end all you have to do is learn that story. That in a rate equation, the order of reaction, which is the power you raise it to in the rate equation, is equal to the number of particles of that substance that react in the rate determining step. And remember, the rate determining step is the slow step if it comes first, or it's the sum of the steps up to and including the slow step if the slow step isn't first. So that situation's a bit more difficult, but this was nice and easy because the slow step is the first step. So really that translates as slow step is the rate determining step, therefore the number of particles of each substance involved in the first step is the order of reaction. So you've got one molecule of aldehyde, which is compound W. W is the aldehyde, will be first order because one molecule reacts in the rate determining step. Cn minus will be first order because one ion reacts in the rate determining step. H plus only comes in the second step. So the rate determining step is over and done with, and then the H plus comes in the fast step, and so that will be zero order. So it only comes in after the rate determining step. Okay, so what you had to do was to either in your head, if you can see the mechanism that clearly, or else scribble it down and say, right, what was involved in that rate determining slow step? One of those, one of those. So that means the rate is always K times first order for W, because there's one of it, first order for Cn minus, because there's one of it, and H plus isn't in the rate equation. The rate doesn't depend on the H plus concentration because H plus only comes in second. Now you absolutely have to know this connection, and you just need to practice applying it. Now, I think that threw a lot of people because it came in an organic question, and your head probably was sort of thinking in an organic way, so maybe you struggled to make that connection. Well, okay, but that's what you need to be able to do, is to take this knowledge and apply it to any reaction like that. And if you know what the mechanism is, you can apply that rule there. So that was the answer.